Welcome back to about information protection under the hood. Today we're going to talk about the SPC generation, and that was a long time kind of a myth. Several people in the last couple of years tried to uncover the important parts of the SPC generation, and I'm going to show you some write-ups I found online. So first of all, Microsoft themselves described the SPC generation, if like you can see it above or down here, the following way. The SPC, which is down here, together with the public key, private key, and the signature, somehow gets protected by both the DP API, short for Data Protection API, and the RSA Vault for obfuscation. We will cover all this in the talk today. And besides Microsoft documentation, they also published in 2019, wait a second, here at medium.com, they published Azure RMS under the hood from Alexei Goldberg's, also together with Enrique Sacchesi. And they described also the process, what's going on under the hood of Azure RMS. And they also described it here in the second and third entry, that there is some magic happened together with the RSA Vault and the DP API. Other people also covered this topic in 2014. Stanislav Zudkov also described it here in the RMS activation process, also with the graphics here. And interestingly, if you look at this image, it's an older version where they use the term UDRM. So when I'm correct, that's all originally from the DRM protection process. So in the late 90s, Microsoft started the DRM process on protecting their media files with Windows Media Player and so on. And from all this, in 2003, they published the first version of RMS and described how enterprise document protection could work. And all these origins, from what I know, originally are from UDRM and the whole digital rights management protection software. So that's what Stanislav Zudkov described in 2014. And also Matt Felton did a good job on describing several things behind Active Directory RMS and Azure RMS. But they didn't get into that much of detail when it comes to that last part about the DP API and the RSA Vault. So let's go and look at this topic. So first of all, let's do a little bit of a recap. So we know from also the documentation online that there is the login process step, where we then use the registry values and the DP API in order to do some magic, which I describe later, and then get access to the private key of the SPC. Important here is that the SPC is independent here, stored from the private key. So if you look at the rights account certificate here and the CLC, we have the dotted line which goes over all of this private and public key pair. The reason for that is that the private key is also stored in that rights account certificate and also in the client license certificate, except for the SPC, where both parts are stored separately. And when we get access to that private key here at the SPC, then we can, of course, decrypt all other private keys here for the rights account certificate and also for the client license certificate. That's something which we didn't achieve in our publication in 2016, where we broke the limitations of Active Directory rights management services. We just misused the API there in back 2016, but now we are capable of doing some more tricks here. So let's come to the next topic. First of all, I did most of my research here with the help of the API monitor, which is software you can get online. So if we go here online again, then we see on rohitab.com, you can download this application. It's really great, and it helped me a lot in order to understand what happened actually under the hood of Azure Information Protection, client side, and also for the rights management services part. So thank you very much for that tool, and I will come to that in a moment and describing what you can do with that software. So let's come first to the results. So if you do an so-called bootstrapping on the client side of RMS, then what happens first is you execute an executable which is called rm activate, and this also executes some function from the Ipc SecProc DLL, and inside of that Ipc SecProc DLL, and that's true for all implementation of Microsoft RMS, Azure RMS, and also Azure Information Protection, there is a certificate chain stored inside of that DLL. You can just grab for the public key, for example. And if you look online for the Microsoft DRM certificate chain, there are plenty of them. And they are all stored inside this DLL. But only the last certificate is relevant here. So the MSDRM desktop security processor certificate is relevant. Why is that the case? So inside of this Ipc SecProc DLL, we have a software VM implemented, which obfuscates the whole process I will describe in a moment. And I luckily got help from students which are very capable of reversing, because that's not what I'm good at. So thanks for that. So what inside the software VM actually happens is we have some public and private key pairs for two different key sizes. So one for 1024-bit and one for 2048-bit. And we were not able to actually get access to the direct private keys here. For the public key parts, that's not hard. You just can look into the binary for that. And when you generate a new SPC on the client side, you also need to know that both the 1024-bit and the 2048-bit are both bounded to this Microsoft DRM Desktop Security Processor certificate, because there are two versions, one for the with the smaller one and one for the bigger key size. And afterwards, what happens is the software VM generates a new key pair, and this key pair is then used for the whole SPC generation. So the public part gets stored inside the SPC, and afterwards it gets signed by the corresponding private key. So if you generate one for the cryptographic mode 1, you get it signed with a 1024-bit private key, and if you generate an SPC for the cryptographic mode 2, then it's signed with a 2048-bit. So afterwards you have the public key, and know that the SPC, because the key pairs here are bounded to this leaf node. It's a certificate chain. You also can verify the SPC because now it's a chain. It's a self-signed chain. So if you remember correctly, I said this process is identical for every implementation of Microsoft RMS. So if you generate one SPC on your client computer and go to another domain, for example, you could also verify it, because this certificate, this private keys, and this private key here are identical to every domain. It isn't that bad actually, because the whole authentication process happens later. But for example, if you can do a Kerberos kind of attack, like pass a hash or something like that, you could actually generate a new SPC, and then with this Kerberos attack just try to includes this SPC in the domain where you drove the Kerberos attack. It's actually not that bad, because if you pass a hash, for example, you also authenticated as a user, so you could do other things, but that could be something you could automatically do in the domain, so that could be also a little bit better or a little bit worse here. Okay, let's come back to the whole SPC generation. Afterwards, what happens here is that the private key with all the details like P, Q, also the public exponent and the private exponent, get encrypted with an AES encryption algorithm. And for that, you actually need a symmetric key. And what happens here is that also this IPsec proc DLL will generate you 48 bytes. So you maybe wonder why 48 bytes. Actually, what happens here is that they use a export function. So if we come back to the word browser here, to the Chrome browser here, what they do is they do a crypt export key function. And this is happening with the help of the base provider. And here you have the private key blobs. So you have, for example, the modulus, you have the first prime, the second prime, and so on and so on. And if you go down here, there is the crypt export key function, which you can use in order to export this private key. And for that, they're using a symmetric key operation to protect that whole construct. So which should be somewhere in here. Wait a second. Okay, I couldn't find it here that far. Okay, never mind. So what they so the original construct of that of this public-private key pair here is that it is a private key blob, and they're using the crypt export function in order to protect this blob, and they're using the 48 bytes they are having here on the right hand side generated, and hash them with a SHA-256. And then the resulting 32 bytes, I think, where they just use the lower 16 bytes and use them as a key into that AES function. And afterwards, this result gets protected again by the DP API and stored inside the registry. In order to protect this DP API blob, you need the master key, and the master key is a special value which is stored inside of your profile folder. And if you never did something with the DP API, there are plenty of explanations online. So if you go back, so one great researcher which did a lot in this area is Benjamin Delpy. You maybe know his tool Mimikatz, so look it up, it's very great. And also Paula Janovic is one great researcher which explained a lot on YouTube, for example. I think she's currently also employed at Microsoft, so she maybe did a very well job on the security of Microsoft and the DP API. So if you just Google DP API, or a YouTube search, you will find plenty of her research talk about it. And yeah, it's a pleasure to hear to these talks. And yeah, so afterwards, there's also a possibility that optional entropy is necessary in this DP API protection process. I did not really find out when the optional entropy is required. I thought once when I did an activation process on one of my computers, but afterwards I never encountered this optional entropy again. But you could also find out if this optional entropy is necessary with the help of the API monitor. I can explain this later. Yeah. But after this protection process, it's stored inside the registry, this value, and it's called MSIPP-MK. I translated MK always like machine key, main key, master key, something like this. Okay, but if we look closer to that process and we want to reverse it, so our main goal here is to get access to this private key in order to reverse this whole protection process of the private key of the rights account certificate and also of the client licenses certificate. And if you go back here from this process step, you can get the registry values, you can unprotect this with the help of the DP API, and then you get to that AES function where you need to do this unencrypt function. And interestingly, you need access to this 48 bytes in order to hash them, or you need direct access to the key which is used here. So what did Microsoft? They used this whole 48 bytes here and encrypted them inside of the software VM. So there is a special function they are calling, and as an input they're using this 48 byte here and do an RSA PKCS1 encryption process, and the resulting bytes of this protection process, they're using a static public key here with the corresponding private key also inside of this software VM. And afterwards, this blob gets protected again with the help of the DP API and is stored inside of the registry. And this value is called MSIPP-SK, maybe for secondary key or secret key, whatsoever. Never mind. So I got help from my reversing students at the Ruhr University Bochum, and they were not capable of getting access to that private keys, but instead they hooked the IPsec proc DLL at a function call where you can unencrypt this MSIPP-SK value when it was unprotected with the DP API. So what they did is they wrote a C++ program and hooked the IPsec proc DLL, and now you can call it with a RSA encrypted value, and afterwards you get the PKCS1 padded 48 bytes out here, and then you can just grab the corresponding payload of this PKCS1 padding and put it into a SHA 246 operation and get the resulting 16 bytes if you cut them. And afterwards you are able to get access to the private and public key. I implemented the whole process in Python script and also with the help of some tools like the hooked IPsec proc DLL. And later you will see that in a live example where I applied the whole process on an Azure information protected Word document, and I was able to decrypt the all values, got access to the unencrypted Word file, could modify it, and then re-protect the whole document. So that was really a pleasure. But before we come to this part, I want to explain a little bit to you how this API monitor works. So I will change the virtual machines here. Wait a second. Okay, so now we have a Windows 10 here. I can recommend Windows 10 over Windows 7 because in Windows 7 they had additional countermeasures in place in order to prevent you from analyzing the whole process. That's some kind of interesting that the current operating system is more vulnerable in quotes than the Windows 7 here. So what do you see here? This is a Ipc Notepad application. It's a sample application which you could use in order to create a protected text file here. So I did some protection process on some simple text files here. So we have to wait a second because my notebook is not that fast. Okay, so what do you see here? You see that we have the content test2 written down into this text document, and it's possible to read for all users here. So they have some templates predefined, and everybody is allowed to read into the read this text file. And so when we come to the background of this whole process, I started an Ipc Notepad application here and started the API monitor. And so what you can see here on the left hand side, there are the API filters which you can select or deselect. I selected the compound modifier, the data access, Microsoft Net, some of the security identity parts, and also the Visual C++ runtime, and they are necessary in order to get access to the interesting functions. So if you go up there, you see some loading of some DLL files, and also what you see is there are plenty of calls. So we have nearly 500,000 function calls here. But luckily for you, I know what to search for. So if we go and press Control F, we can just enter crypt unprotect, and then we go to the first function, which actually get executed at number 20,462. And what this crypt unprotect function actually does is it's decrypting the MSIPP-SK value. So if you go into the registry and go to computer, current user, software, class, local settings, software, Microsoft, MSIPC, then you will find this very interesting values MSIPP-SK and MSIPP-MK. And then you can also do a little search for another value. Wait a second, I have to think. Data, I think it was this way. Okay, now. So if we go now to Microsoft and not protect, that was for the DP API, but instead, give me a minute. I think it was something different because we are not in the Microsoft. Yeah, okay. So that's kind of an interesting part here. If you're using a non-Word or Office protection mechanism, you will find it under local. So I think it was under local, yeah. And here you see the different kinds of certificate licenses. So the EUL are use licenses for different documents. This cert for 2048-bit is the SPC part for the 2048-bit key algorithm, and the cert machine without any extension here is for the 1024-bit variant. And then we have the CLC, so the client licenses certificate, and also GAC is a different name for the rights account certificate. So that's everything we need here. And yeah, so let's come back to the API monitor. So I want to explain to you how this MSIPP minus SK value gets unprotected. If we go through this call process, just for an explanation, I did for the whole process of getting information out of this unprotect and protect process, and in order to find out what actually happens here, I just did like around 50 of this protect and unprotect processes and just looked at them at the whole API calls. And after a while, I just saw what happened here. So first of all, you see this mem copy value. So if you ever need to understand this kind of DP API process, be sure to just tick the corresponding memcopy, memset, memReset values in order to really find out what happened here. Because if you just look at this crypt unprotect function, you will see that there are some calls with some parameters. And if you are doing this on a live target, so the current executable is still running, then you could do a breakpoint. So for example, you could just break before call or after call, and then look into the memory location. So you have some PB data out inside here or PB data in, and then you can look at the corresponding address and find out what actually happened here. So sometimes it's also stored after the executable was killed. So we see it here also in the stump value, but if you do it on a live example, this has some benefits. For example, if the byte area you are copying or interested in is longer than 1 kilobyte. So API monitor has some limitations how much of data they are recording. So doing it on a live example sometimes is more interesting or get you more information. So we now see this really interesting structure, which is very prominent for the DP API. And if we just look at this 4 bytes on the last part, and if we go back to on our MSIPP-SK value, we see that the values are pretty similar at the beginning. But if we open it and go back to the last part, we see that this 4 bytes are, so the last bytes here are identical to the one we saw in the API monitor. And yeah, so that's what's happening here. So we have this crypt unprotect function, and this 276 bytes get later unprotected to this 136 bytes. And this is pretty close to an RSA modulus of 1024 bit. So there are 8 byte which are unnecessary from the whole decryption process, but this 136 bytes go into this virtual in this obfuscated software VM inside IPsec proc DLL. That's also the reason why you don't see it here. And later, you just will see that there is some hashing happened. And that was what's bugged me all the time, because I saw this 136 bytes, and later, if you go down here, you will see that there is some hashing happening. And I was really confused why there is this hash function, and how this process step happened from the memcopy here with the resulting unencrypted, unprotected value, but then the hash just popped out of nowhere. So that's where my helpful students came into place and told me what happened actually in the IPsec proc DLL. And if you copy this value here and put it into a SHA-256 operation, so I prepared it here. So 6E, F2, F0, and so on and so on. So 6E, F2, F0, and so on and so on. And we go down here to this function. We will see that the resulting hash function value is DD, and at the end A5, F3. And we can look it into this here, DD 51, and at the end we have A5, F3. So that's the 32 bytes from the output of the SHA-256 value, and the resulting one is then the DD until BC A2. That's the 16 bytes they are using in the script derived key function, which is the import corresponding to the export function. And later they have the the public and private key pair. In order to do that, they first need to unprotect the RSA key pair, and it's happening here the same way as before. So this whole memory part, which is the input here, so we can look into that again. We have B2, BC, 3F. If we go here, we have, and that's what actually, don't wonder. So the registry editor does not show you all values. So you see it's somewhat limited. If you export the function, the whole data type, for example, we can do that here. Wait a second. Export. Okay, so let's do that quickly. MK. Okay, now we should see that value here. And if we go on edit and go down here, we see, so we had, yeah, I'm quite sure that's not the whole, yeah. So you see 1024 bytes were showed in the text buffer, but we have actually 1324 bytes which are copied. So that's the reason why I told you last time that we need to do a live analysis so we can jump into the corresponding memory area and look at the actual values. But I can promise to you that this is actually the MSIPC value. So this is the RK value, okay. If you do the export, it's exporting every value here. So we have the AC, and that's the MSIPP-SK value here. And then we see the MSIPP-MK value here. I normally use the Notepad++ application in order to do a hex string out of that. And then we can use this with the data protection decryptor, for example. I show it to you in the next live video where I unprotect this file. Okay, so we now know how this RSA vault actually works. We saw that it's just an RSA operation with PKCS1 padding for encryption and decryption, and that they use a SHA-256 operation and use the last 16 bytes in order to protect the private key and public key of the SPC. So I will switch the machines again. So what can we do now? With the access to this actual private key here, we can do the whole unprotect process. And if we go backward, okay, so if we go to this example here, maybe I should use, I use this one. Okay, so that we now have access to the private key of the rights account certificate and also to the private key of the CLC, we actually can generate new publishing license because we can create the signature here. We can get access to use licenses content keys because they are encrypted with the public key of the rights account certificate. And yeah, that's pretty much everything you need to do in a Active Directory domain or with Azure Information Protection in order to do bulk decryption of protected files. You could create new files with new content. And here comes the problematic part of the whole Azure Information Protection AD RMS. So Microsoft in the last year said It's not intended by our implementation to protect you from content modification. They talked to their customer and it was not that high priority for them to have this content modification detection or authorship. And yeah, that's somewhat, not good because we are in 2020. And for example, WhatsApp is more secure than this enterprise documentation protection process. So that's some kind of not good practice here. But yeah, it's their decision. It's their customer they are protecting. And with these videos, I also want to show to their customer where the limitation is, because before we started our publication, they normally we're just talking about we have RSA signatures, public key encryption, and AES, and that was everything you knew about Active Directory rights management services and Azure RMS and so on and so on. And they still using AES with electronic codebook mode or CBC mode, so that's also not crypto you should use in 2020. After we published our first attacks, they told us, it was never intended that we have this content modification detection or protection. But on the other side, they never told anybody that this protection process is not intended by the software. So what you could do if you here to Microsoft, you could just use signing for Office documents. So if you open your Word application in the enterprise context, you can also do SMIME signatures when I'm informed correctly. So, but you also need for that one new certificates and from other parties where you have to pay for. And from the eFail publication and so on, we know that SMIME signatures and in general signatures which are not integrated that much into an Office suite are probably a bad idea. And so if every customer is informed about this limitation, let's just name it limitation, that would be great, because if you go to Microsoft website and look at their customer, let's take a look. Azure Information Protection. Let me look into it if I find it in a moment. Okay, I will pause this video here and come back later. Okay, I found the website. So if you go to customers.microsoft.com, you can search for Azure Information Protection, for example. You could also search for Azure Information Protection P1 and P2 because they have different pricings for that. And if you look at the customers, you see, for example, German Exchange Group. You see some universities, police stations, consulting companies. Atos is a big company for security. Some car manufacturer, also Vodafone, some insurance, and so on and so on. And also here some German manufacturer. And the question here is, do they all know what actually the limitations of Azure Information Protections are? So we have also banks inside here, and so on and so on, some police stations. And now just imagine we have, let's do a federal police station here. Let's do the example that we have some file which is protected with Microsoft RMS, and you modify the content and reprotect it. So there's no possibility, I have to repeat that, no possibility that you could find out if the author of the document really created this document just from looking at the Microsoft document, which was protected. So if you have other mechanisms in place like versioning of files or when the file were accessed. Then you could maybe find out which modified the document last time, but you could also just modify the whole content of this document. And if you do it with a simple editor, it's also not possible to see the difference here in the Word file. So for example, if you open up just the normal Word and you do it with an empty document here, then normally if you go to File and then Information, you see the author here. And you can unprotect an RMS file, modify the content without actually modifying the original author. So if you open up the unprotected Word file with Word and edit this one, then the author also get changed. But if you're using, for example, a simple editor application, then it's still the author here of the original created protected Word file. And in this case, you could just say, okay, release the prisoner or what else, just imagine it. And that's something which everybody should know, that this is a very big limitation of all implementations of RMS, Azure RMS, or also Azure Information Protection. So that's everything for today. Thank you very much for your attention, and see you in the next video where I will show you how actually unprotect, protect and modify the RMS Word files.